In part 5, we will touch upon the next sampling mechanism, stratification. As you remember, stratification is used in, for example, the Belgian Health Interview Survey. First, by splitting the population into Flanders, Brussels, Wallonia. Second, by further splitting Flanders into its 5 provinces, Wallonia into its 5 provinces, and then also splitting off the German-speaking community, which means that we end up with 12 strata altogether. We do recall also that the selection probability is not the same in all of the strata, in the sense that Flanders, Brussels, Wallonia and the German community have a different selection probability indeed. But that is a side effect of the stratification procedure that was followed. Of course, it's an important side effect and it should not be neglected. It should be properly taken into account. But before we are at taking things into account, it's better to gently go through the concepts, the principles, what is stratification, and like always, why do we use it, question mark, what impact does it have on precision, does it always have the same impact, etc. So that is what we will start touching upon from chapter 13 onwards. So, why do we do it? Why is stratification done? Well, one of the major reasons to do stratification is to make sure that your sample is sufficiently well spread, so well mixed across your population. Otherwise, it may well be that just by pure chance, you have a larger fraction of people from Limburg and a smaller one from Antwerp, or vice versa. Well, if your sample is large enough, that's usually not going to be a problem. But in smaller samples, smaller populations, but especially smaller samples, that may be the case. So it's there to ensure that two extreme samples, like all moves to one side, all moves to the other side, cannot happen or cannot happen so easily. It should be clear that we don't do this for bias reduction, because if a sample by accident has more people from Limburg, less from Antwerp, then in the same way it could be the other way around. So across all possible samples, it would still average out to the right quantity. So it's not a matter of bias. But as we've said repeatedly, it's not so much bias versus variance that's of interest to us, it's a combination of the two. So if there is a big discrepancy between the estimand in the population and between the quantity that you have found from your sample, well, if that's because of bias or because of large precision or large variance rather, you don't care, you're unhappy with the situation either way. So whatever we can do to reduce the discrepancy between what we observe and what is the true population quantity is relevant. In the same way was benchmark estimation considered, because benchmark estimation, well, it sometimes introduces a little bit of small sample bias, but it may drastically reduce the variance. So therefore, overall, its impact on the mean square error is great. So, ways of compensating for that, as I said, benchmark estimation. The further one I would like to mention is systematic sampling, where we create a list, we cycle through the list, make sure that, for example, smaller, medium-sized and larger units are all represented in a fair fashion. That reduces the sampling variability. Stratification often reduces sampling variability. It's one of the major reasons. Benchmark estimation, the same story. But as we will go through the material, we will see that there is another reason for stratification, and that is when you want to say something about the strata. So that puts a little bit of a different perspective on the reasons to do stratification. There is not one. There are two different ones, and that is reducing the variance, increasing the precision, that is. One. Two, it's sometimes done because we want to make sure that the strata themselves are open for inference, that we can draw conclusions about the strata themselves, that we, in other words, can say something not only about the health of the Belgians, but also about the health of the Flemish, the Brussels, the Walloon, and the German-speaking people. And yes, maybe in some provinces as well. And as we will see further, these goals are sometimes conflicting. You cannot really make sure that your sample is absolutely optimal for both at the same time. That doesn't need to be a problem, but it's an issue that requires some attention. Okay, so how does it work? You partition your population. You say everybody belongs to one and only one stratum at the population level. And this is before you even start taking a sample, before your survey. So you basically say at the level of the Belgian population, the 10 million people that we usually use for simplified reasons, 6 million of them belong to the Flemish strata. And then later, maybe, let's say, roughly 500,000 or a little more belong to the Limburg stratum, etc. That's at population level. And then, second, we draw samples from each one of those populations. So, simply said, if you take a population and you split it into 2 strata, and then you say half of my sample is taken from stratum 1, half of the sample is taken from stratum 2, it's simply no longer possible that everybody comes from the same stratum. You made that impossible by the design that I sketched. So, like with systematic sampling, the probability that a certain extreme sample occurs is set equal to 0. You reduce the probability of not so well balanced samples, and you entirely reduce it to 0 for the very unlikely samples. Okay. Stratification, when does it work well? So a little bit like with a benchmark estimation, that is the survey variable should be positively related with the stratifying variable, like with the benchmark. So if there is a health difference between Brussels and Flanders and Wallonia, for example, excuse me, more people have a stable GP in Flanders and Wallonia than in Brussels, which is the case. Well, stratifying for region will beneficially impact your precision, because you will make sure that not by chance you have more people from Brussels and that would bring the estimate down, or more people from Wallonia that would bring the estimate up. No, you make sure that it's not more or less, that it's exactly the right proportion, and that source of variability will be excluded. So variability, because of different sampling fractions across the strata, is made impossible, is removed. Okay, so what are the usual suspects? Well, those socioeconomic and other variables that tend to correlate, that tend to go together with many survey variables, like especially health-related is often age-dependent, gender-dependent, geographically dependent, but that's often a proxy for culture, size of units, socioeconomic status, educational level, occupational status, type of activity, etc. So, we may now think the more the merrier. The more stratifying variables we choose, the better it will become. But there is the fallacy, the myth, the curse, as it were, of multiplicativity. The more stratifying variables you use, the more strata you're going to have, evidently. But that's multiplicative. So let me give you a simple example. Suppose that we say, oh, Belgium is large, the Belgian Health Interview Survey is large, so we can afford to take these 8 stratifying variables. And let's for a moment not think and say, okay, we divide the population in 5 age strata of 10, 15, 20 years, 2 sexes, 12 geographical entities, 5 different sizes of units, households of 1, 2, 3, 4 persons, 5 or more people. Socioeconomic status, let's say 4 levels, education, 4 levels, occupational level, 4, and then type of activity of education, 5. If you multiply all of that, so 5 by 2 by 12, etc., you get to 192,000. Now that's a little bit of a problem for a sample of size 10,000. 10,000 is large, but the number of strata is 20 times larger than the number of people. So it's completely impossible, right? It would mean you have 0.05 person per stratum. So you have to be moderate with the number of strata that you consider. Okay, so that's what I just said. We have overstratified. We scale back and we say important stratifying variables at not too many levels. Let's stick to that. Let's stop it there. Okay. A very important message that I've brought before is there are two different goals for stratification. One is to increase precision. So we're interested in Belgium, but we want the estimate at Belgian level to be precise, not haphazard, not variable, because we move from a sample with more people from Flanders to one with less people from Flanders from one year to another. No, we keep that fixed, and that leads to more precise results. The second goal is, as I said, we want to say something about Brussels, Wallonia, Flanders, the German-speaking community, etc. And therefore, we ensure a minimal sample size. And sometimes, even the goal is to compare regions. Well, for comparison of regions, equal sample sizes are actually better. Or just if you juxtapose, if you put the results next to each other, it's easier that Flanders, Brussels, Wallonia would have the same sample size, because that implies roughly the same precision. For example, on the body mass index, if you have more or less equal length confidence intervals, comparison is easier. We discussed that before. So what I'm already saying is, for goal 1, it seems more appropriate to do a proportional allocation. For goal 2, it seems to be more appropriate to have equal allocation. Now, that's more or less truth. The actual result is subtle and there are some mathematical details, but the big picture will remain. For goal 1, it's better to have proportional allocation. So 60% Flemish people, 30% Walloon people, etc. For goal 2, it's usually better for all sorts of comparison reasons to have equal sample sizes. So, for example, 1/3 from Flanders, 1/3 from Brussels, 1/3 from Wallonia. But of course that's not possible two at the same time, which is why we will sometimes need a compromise when both goals are on the agenda at the same time. Okay, what quantities do we have? What describes our population and our sampling mechanism? Well, the population units, population size, the sample size, whether we sample with or without replacement, and that's the same as with simple random sampling. But then we continue and we say we have H strata, for example, the 12 provinces or provincial entities. And then we do the same thing, but now at stratum level, NH, the number of people living in a given stratum. Capital N is the sum of all the NHs. YHI, and look at the lowercase h for the stratum indicator, but the uppercase I for the population unit indicator. Well, that's indeed person I living in, for example, the province of Vlaams-Brabant. Okay, so we have defined subpopulations. In other words, we have taken the population, we've brought out scissors, and we've cut up the population in strata, and then we have everything that we normally have for the population at large, now also in every one of the strata separately. NH, the sample size. The total sample size is the sum of the stratum-specific sample size. That's pretty evident. If Flanders gets 6,000 people in the sample, we can take that example, yes. Wallonia 3,000 and Brussels 1,000. The sample size is overall 10,000. If we use 3,500 people from Flanders, 3,500 from Wallonia, and 3,000 from Brussels, the sample size N is 10,000. But it came into being in into two different ways. The sample fraction can be the same, and that's proportional allocation, or it can be different. For example, with equal allocation, but that's not the only example. Well, with equal allocation, NH will be a constant, lowercase NH will be a constant. Uppercase NH will still vary from stratum to stratum. For example, we may take 3,000 people from Flanders, or let's make it 3,500 from Flanders out of 6 million. But in Wallonia, it will be 3,500 equal out of 3 million. So that means the numerators are equal, the denominators are different, so the ratio is different, the sample fractions will be different. Okay. Sometimes we look at the sample size vector n, which is all the sample sizes, one listed next to the other. Okay, so if you say n is equal to 4, 3 in a stratified exercise with 2 strata, this means we have to select 4 people from stratum 1 and 3 people from stratum 2. How many possible samples can we have? Well, you calculate the number of samples per stratum and you just multiply that. If in stratum 1 you can take 5 samples, I'm just making up the numbers, in stratum 2, 7, then you have altogether 35 possible samples, because every one of the 5 samples in stratum 1 can be combined with every one of the 7 samples from stratum 2. And these are 2 different samples because strata have to be disjoint, nothing in the intersection, which means you simply multiply. Okay, few examples. You have a list of school children. You may stratify according to school district, study year, and then select 10% out of every stratum. That would be proportional allocation. So you have a 10% sample overall and in each one of the strata separately. Okay. Now, an important difference that can occur is between pre- and post-stratification. What we have been discussing and what we called stratification, nothing more than stratification, is actually pre-stratification. We stratify by design. We divide the population into strata and we decide on the sample size that we take in each one of those strata. And then, after the design stage, there comes the analysis stage, whereas we always say there should be a link from design to analysis, so we should take this into account. So if you do both, that is classical stratification. If you do none of the two, that's actually simple random sampling. You could also do something else, and that's say, I will not stratify at the design stage, but I will stratify in the analysis stage. So that is post-stratification because you only do it at the end, not at the beginning. The other way around, where you stratify by design, but you don't do that at analysis, that is simply said a mistake. That is problematic, unless that there are cases where you can motivate that it's really not necessary to correct. Usually a correction is needed. Okay, there are exceptions to that. For example, in randomized experiments, you can stratify in the design and not take that into account in analysis. But in observational studies like in epidemiology or in surveys, not taking a stratifying variable into account that you use during design stages is usually incorrect and would lead to biases. Okay, but post-stratification is not necessarily biased, it usually isn't, but why do you do it then? Well, you may see that there are important variables that are strongly related to the survey variable and that imply a differential result. For example, males and females may respond differently to certain variables, but you did not stratify for male and female at design stage. When you took the sample, well, it's then possible to go to the very end and conduct post-stratification, which is in the analysis stage, you stratify for gender, and then later you may combine the results again, but you didn't do it a priori. That is post-stratification. Now, if you do that, you may wonder, why, if I can do it at the end only, why do I make myself tired by doing it already at design stage? It's not needed. Well, we don't say that. You can do it at the final stage only, but the right question to ask is, do we suffer from it? Do we pay a price? The answer is, yeah, but mildly. The thing is, if you pre-stratify, for example, according to region, you fix the sample sizes per region. There's nothing variable, nothing random in the number of people from Flanders. Well, there is a little bit rounding, of course, because of missing data, and but you get the point. We get very close to the 6,000. If you leave it to chance, the sample size per region is going to be variable. It becomes a random variable, and that random variable has variability, and that variability comes into our estimator at the end. If you post-stratify, you may want to take into account different relationships, different averages, etc., across different levels of your post-stratifying variables, but you didn't do anything to make sure that the sample size over the various levels of post-stratification is the same. In other words, if you pre-stratify for gender, you decide on a 50-50 split. But if you post-stratify for gender, it's not going to change the fact that your sample happens to be 44 men and 56 women, even though you wanted more or less 60%. So there is some room for it, but it's still technically, in terms of performance, less optimal than pre-stratifying. Okay. All right, so having that in mind, the problematic case really is, the one that you should avoid is, you do stratify in the design stage, but you do not take that into account at the analysis stage. It's problematic for surveys, for retrospective case control epidemiological studies, it's problematic. The one place where it's slightly less problematic is in randomized clinical trials, as I've already indicated. Okay. With that said and done, let's go for an example, and let's take something very simple, now the artificial population with 4 units. So indeed, my 4 units, I'm going to stratify them into obvious strata, natural strata, 1, 2, and 3, 4. And obviously, I'm going to take samples of size 1, 1, which means 1 unit from the first stratum, 1 unit from the second stratum. Well, we will write it down formally, cleanly in a moment, but very informally already. That would generate sample 1, 3, 1, 4, 2, 3, 2, 4. How many samples are there really? Well, I could also draw 1, 2, and 3, 4, but these two get probability 0 right now. That cannot happen. So I'm using my units information, but I make sure that the units that I bring together are not too extreme. And that has the same impact as we discussed of systematic sampling. We also saw similar impact with benchmark estimation, where something like this could be happening, 1, 2, and 3, 4, but we will fix it up at the end. Here, we avoid the problem at the baseline, at the root. Okay. Another stratification would be, guess what, 1, 4, 2, 3. That's another one that we can think of. And a third and last one is actually 1, 3, and 2, 4. Okay. So we take a sample of size 1 and 1, one from the first stratum, one from the second stratum. The mechanisms are, as I said, 1, 2, and 3, 4 are impossible. Well, not with simple random sampling, but now, yes, now they get probability 0. So the most extreme samples are taken out of the loop. Whereas, if we go for the second somewhat bizarre stratification, is the middle ones that go out of the loop, 1, 4, and 2, 3. And that's not necessarily a very good thing. Okay. Stratification 2, PS2, is stated to be outright bad because the effect is that the most extreme samples are nicely possible, and the more moderate balanced samples, where something large compensates something small, are taken out of the equation. So that's not really very good. Okay, now let's produce the estimator under the good schematic, the correct schematic. Well, the expectations over the averages, they're like 2, 2.5, 2.5, and then, sorry, here, should write it better, 3, the average is 2.5. For the second, I get different numbers because there are 4 different samples, but they also nicely average out. But I do see that here I have a smaller value than any value here, and here I have a larger one than every value here. So it must be a little more variable. So let's calculate the variances and add it to what we have used before. So simple random sampling without replacement, we got a variance of 0.42. Simple random sampling with replacement, it's 0.625. The lists that we used before, you remember there was one very extreme list. For one list we did well, we went down to 0.25. For the other, we slightly less, for the other one, it's slightly higher. So this is not so good a list, this was a very good list. And now, here, we add two of the two equations, one for the good stratification, S1, and one for the poor stratification, S2. 0.125, it's gone down, and the second one, the not so good list, is actually the same as simple random sampling with replacement, and we know that is not optimal, of course. So, some lists decrease the variance, others increase, likewise. Some stratifications decrease the variance, and that's usually what we want and what happens, but others, especially in artificial, but say more generally, small populations, you might see the reverse. Okay, let's try and see what happens in Survey Town, where we have the X and the Z that we used before in benchmark estimation. So, the list that we considered are the list of X, 1, 2, 3, 4, 5, 6, 7, 8 with the units. For Z, it's 2, 6, 5, 3, 7, 1, 4, 8. Good, and let's now stratify. Let's go to the middle of the list and chop them both off. So 1, 2, 3, 4, 5, 6, 7, 8, but also 2, 6, 5, 3, 7, 1, 8, 4. All right. So, if we select samples of size 2 in a 1-1 fashion, we take, for example, in the first one here, 1 unit from one and combine that with 1 unit of the other. There are 16 possibilities, right? Because 4 units, you take 1, 4 possibilities. 4 possibilities also on the right-hand side, 4 times 4 is equal to 16. And the same with the other one. So here they are. These are the 16 ones that are possible for X, and these are the 16 ones that are possible for Z. Okay. So, here are all the samples, and we recall now, because we've seen it many times, that we always need 2 pages, of course, because there really are 28 heterogeneous samples of size 2, 1, 2, 1, 3, ... until we finally get 7, 8. So under simple random sampling, they have each probability of 1/28. If we go for the lists in systematic sampling, we jump through the list and only now and then do we land and we have a sample with probability, a sample that's taken with probability 25%. If we stratify, there are 16 possibilities, so 16 of the samples will get a probability of 1/16, and the other ones, like 1, 2, it cannot result from the stratification that we have. Typically, not a lower number with another lower number, or a higher number with another higher number. Well, if we look at the possible values with X and with Z, what do we see? The variance under simple random sampling is 144. If we do systematic sampling, the variance goes down to, and I look at dimension 4, I will look at systematic sampling first with list X. It went up to 80, and with list Z it went down to 32. It didn't go up, it did go down to 80, but with list Z, remember, list Z was a little bit of an anomaly. It did work well in spite of our expectations. So with systematic sampling, yeah, 80 is better than 144, but 32 is even much better than that. With stratification, the list X, which we consider a good list, brings the variance down to 40. That's a good reduction over 3 times. But list Z, the other stratification here, produces a marginally bigger variance of 166. Okay, so that is how we calculate the variances by just doing the job numerically. Good. Homogeneous strata. So what do we mean by homogeneous strata? Strata where the units within a stratum are more alike than between strata. Like people in Brussels are more similar than people, let's say, a few in Brussels and a few in a rural area, just because of that maybe. So there's more homogeneity. So if you then stratify and take a little bit from all of the pieces, you have a sufficiently heterogeneous sample, because if you take homogeneous strata, but you take from various strata, you make your sample heterogeneous. It spans the population. It has medium size, large, small values, etc., and therefore nicely averages out. Okay, that brings me to the end of chapter 13, which is the concepts, and then as usual in chapter 14 we move on and see how we can conduct estimation, draw inferences when we have a stratified sample.